Okay, we've talked about the number of divisors function, tor, or d, and now I'm going to consider sigma of n, which is another number theoretic function, equals sum of divisors function. So what it is equals sigma of n equals the sum of the divisors of n. So let's sigma. It's a sort of Greek sigma. Sigma of 12, always a nice one. Well, what goes into 12? 1 does, 2, 3, 4, 5 doesn't, 6 and 12 itself. So what have we got? 1 and 2 is 3, plus 3 is 6, plus 4 is 10, 16, plus 12 is 28. Sigma of 12 equals 28. Before I start going on about this, I'm just going to make the observation that a perfect number is one where sigma of n equals 2n. Because for a perfect number, you count the sum of the divisors of n. N is a perfect number if the sum of the divisors of n, excluding n itself, equals n. And sigma of n, this number theoretic function here, which for good reasons, as we'll see in a few minutes, for good reasons includes n itself, has got an extra n in there, so there's 2n. So for example, you say that 28 is perfect because the divisors will be 1, 2, 4, 7 and 14, so plus 28. So sigma of 28 equals that, but the perfect nature of 28 is these sum to 28 here, so that these kind of match. So sigma of 28 equals 28 plus 28. So sigma of 28 equals 2 times 28. So it's a little bit of a peculiar definition of a perfect number, but there it is. Okay, so how do we work out what sigma of a general number is? Well, what we're going to do is write it out in prime factors. We're going to work out sigma of p1 to the alpha 1, p2 to the alpha 2, pr to the alpha r. How on earth do we work that out? Well, what we do is we consider this. We consider the product 1 plus p1 plus p1 squared plus p1 cubed plus blah 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 up to p1 to the alpha 1 times, I'm going to pinch in a little bit here, I'm going to run out of space, 1 plus p2 plus dot 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 plus p2 to the, what's its power, alpha 2, times all the other similar brackets times 1 plus pr plus dot 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 plus pr to the alpha r. Okay? And we're going to observe that this product here, well, which one do we take? If we take, well, let's have a look at a term will be p1 to the power something times p2 to the power something else times this times this times this, which is the divisor itself. So this large polynomial here, or potentially large polynomial here, each positive divisor of n appears once and once only when you multiply this great big thing out here. Okay, it takes quite a lot of time. That's quite a profound observation. There's quite a lot going on in there. This is why it crops up in mathematics Olympiads, because there's quite a lot of meat in this observation here. I'll just take you through that again. If we have a look at an individual term in here, any individual term when you multiply this thing out here, any individual term will be a divisor of n. And of course, when you have the whole polynomial multiplied out, you will have the sum of all those divisors, which is what we're trying to do. So if you take the last term in each of these brackets, the last one in each bracket, you'll have n itself. And if you take the first one you'll have 1. and because we're adding them all together we get the sum of the divisors. Well, this isn't very useful as it stands, but I'm just going to rewrite that as this. I'm going to rewrite that as P1 to the alpha 1 plus 1 or minus 1 over P1 minus 1. That's just a sum of a geometric series. Times the next one, P2 to the alpha 2 minus 1 over P2 minus 1. Note that this is well defined because prime numbers are greater than 1. 1 is not a prime number. Here's another reason for 1 not being a prime number. Multiplied by all the other terms similar, times PR alpha r minus 1 over PR minus 1. Okay, well that's nice, and this is sigma of n, where the prime factorization is sigma pi to the alpha I equals this. Equals the product from I equals 1 to r of pi to the alpha I minus 1 over pi minus 1. Neaten that up a bit. I minus 1. Brilliant. So we can do a nice example here. We can work out sigma of, let's say, 180, which I certainly couldn't be bothered to do. And we got the prime factorization of 180, didn't we? It was 2 squared from the last screencast, 3 squared times 5. Yeah, that's right. So P1 equals 2, alpha 1 equals 2, P2 equals the second prime is 3, alpha 2 equals power 2, P3 equals 5, alpha 3 equals 1, because it was 5 to the power 1. So let's just do this. Let's work out what sigma of 180 is. Equals. Oh no, I need. There's a plus 1 I've missed off there. Plus 1. Sorry about that. Sorry about that. That should have been an alpha I plus 1. Okay, well let's just do it anyway. So it's 2 to the power 3, because it's 2 plus 1 minus 1 over 2 minus 1 times 3 to the power 3, because it's 2 plus 1 minus 1 over 3 minus 1 times 5 to the power 2 minus 1 over 5 minus 1. Yeah, that's right. Equals, that'll be 7 over 1 times, that's 27/26 over 2 times 24 over 4. Can we do any clever cancelling? Well, a little bit. 13, 1, 6. And so we've got 7 times 13 times 6. 7 13s are 91 times 6. 9 6s are 54, 546. So sigma of 180 equals 546. And it should be pretty, it should be obvious to, well, we can use that formula. But sigma of p, if p is prime, sigma of p equals 1 plus p, I guess. Well, there you go. Well, we could have used the formula if we want, because it's p squared minus 1 over p minus 1, p minus 1, p plus 1 over p minus 1 equals p plus 1. So we could have used that formula there. These formulas for sigma and tau are very, very useful. There's a lot of meat on that. This argument here, this argument about adding up the divisors, summing the divisors, is a very profound argument indeed. There's a lot going on in that. It's worth going through this this over and over again. I'm going to make a separate set of screencasts all about generating functions like this. Yeah, and because that's quite a difficult thing, because this polynomial is quite a hard one, this formula for sigma of n crops up very, very, very frequently in Olympiad questions. So there it is. And I'm going to stop there.